In December 2004, an explosion 50,000 light-years away hit Earth's atmosphere hard enough to ionize the ionosphere and disrupt shortwave radial across the entire daylit hemisphere. No nuclear weapon produced it. No human mechanology detected it coming. It lasted 0 per 10s, 2 seconds. Here are 6 events that show what real violence looks like at cosmic scale, starting with number 6. Number 6. Gamma-ray bursts. Gamma-ray bursts are the most energetic electromagnetic events in the universe. For anywhere from milliseconds to several minutes, a single burst puts out more energy than the sun will produce across its entire 10 billion-year life. There are 2 mechanisms. Short gamma-ray bursts, under 2 seconds, happen when 2 neutron stars collide, or when a neutron star merges with a stellar mass black hole. Long bursts, over 2 seconds, happen when the iron core of a massive fast-spinning star collapses directly into a black hole, a process called a collapsar. The whole transition takes milliseconds. A jet of gamma radiation then punches out through the collapsing stellar envelope and escapes. A typical long GRB releases about 1044 joules. That is the total energy the United States would consume at current rates over 1027 years, which is a number so far outside any physical reference that the analogy tells you nothing. The most extreme event ever recorded came on October 9, 2022. Cataloged as GRB 22109A and nicknamed the BOAT for brightest of all time, it was picked up simultaneously by NASA's Fermi Gamma-ray Space Telescope, the Neil Gehrels Swift Observatory, and the Chinese InSight HXMT satellite. The burst came from a galaxy about 2.4 billion light-years away in the constellation Sagitta. Its peak flux was 50 times greater than any previously recorded GRB and saturated the detectors of every gamma-ray telescope then operating. Its afterglow stayed visible in optical wavelengths for more than 3 weeks. Number 5. Magnetar Giant Flares. A magnetar is a neutron star with a magnetic field roughly 1,000 times stronger than an ordinary neutron star. Ordinary neutron stars already have fields around 100 billion times stronger than Earth's. Magnetars form in supernova explosions, and in the centuries after formation, the crystalline crust can fracture and shift under magnetic stress, releasing the tension in a flash called a giant flare. On December 27, 2004, a magnetar called SGR 1806-20, about 50,000 light-years away in Sagittarius, released what is now considered the most powerful burst of energy ever observed from outside the solar system. In about 0.2 seconds, it emitted more energy than the sun produces in 250,000 years. It ionized Earth's upper atmosphere, registered on spacecraft that were not even pointed toward it, and disrupted low-frequency radio across the entire sunlit side of the planet. The Rossi X-ray Timing Explorer and the RESE satellite were both partially saturated by the event from 50,000 light-years out. Kevin Hurley of UC Berkeley led the initial analysis, published in Nature in February 2005, and concluded that the peak brightness was still a lower bound because the detectors had gone blind before the maximum was recorded. Teruaki Enoto of Kyoto University later used archival data from multiple spacecraft to put the energy release at a minimum of 2 pi-1046 ergs. Number 4. Hypernovae. When an ordinary massive star dies, it explodes as a supernova and leaves a neutron star or black hole behind, releasing around 1044 joules. When a specific class of very massive, very fast-spinning star dies, the collapse is faster and more complete, the jet is more powerful, and the result is a hypernova, putting out 10 to 100 times more energy than a standard supernova. The stellar type most strongly associated with hypernovae is the Wolf-Rayet Star 1 that is burned through its hydrogen envelope and is exposing its bare helium and carbon core to space, usually spinning fast enough to generate the angular momentum needed to drive a jet through the collapsing material. The first confirmed hypernova was SN 1990 ADW, found on April 25, 1998, in the constellation Telescopium and directly linked to gamma-ray burst GRB 98425 by a team led by Titus Galama of the University of Amsterdam. That association, published in Nature in June 1998, changed how astrophysicists understood both supernovae and gamma-ray bursts at once, showing that at least some long GRBs come from hypernova events inside star-forming galaxies. The kinetic energy of SN 1990 AW was around 5 by 1052 ergs, roughly 50 times the standard supernova output. Closer to home, the star Eta Carinae in the constellation Carina, about 7,500 light-years away, is considered a prime hypernova candidate. It already had a major eruption in 1843, briefly becoming the second brightest star in the sky. The Hubble Space Telescope's Treasury program has watched it continuously since 1999. Number 3. Quasar jets. A quasar is the extremely bright nucleus of a distant galaxy where a supermassive black hole is actively eating surrounding matter at extreme rates, converting the gravitational energy of infalling gas into radiation at up to 42% efficiency. That is more than 4 times more efficient than nuclear fusion in a stellar core. Some quasars also launch twin jets of plasma perpendicular to the accretion disk at velocities between 0.99 and 0.99. 99 times the speed of light. These relativistic jets stretch hundreds of thousands of light-years and deposit energy into the surrounding intergalactic medium at rates that can shut down star formation across entire galaxy clusters. The most studied jet system belongs to the elliptical galaxy M87, formerly Virgo A, about 55 million light-years away. M87's jet extends about 5,000 light-years and was first photographed in 1918 by Heber Curtis at Lick Observatory, the oldest observed astrophysical jet on record. In April 2019, the Event Horizon Telescope collaboration published the first direct image of a black hole's shadow, showing M87's central mass at 6.5 billion solar masses surrounded by a bright ring of plasma that feeds the jet. The Quasar 3C 253, the first quasar ever identified, found by Martin Schmidt at Palomar Observatory in 1963, has a visible jet extending 200,000 light-years at relativistic velocities. The mechanism by which a black hole's rotation extracts energy to power the jet, called the Blandford-Znagit process and theorized in 1977, was only directly confirmed by Event Horizon Telescope data published in 2021. Number 2. Kilinovae. On August 17, 2017, at 12:41,004 UTC, the LIGO and Virgo gravitational wave detectors picked up a signal lasting about 100 seconds. That is far longer than the brief 0-tubble-second chirps produced by binary black hole mergers. Within 2 seconds of the signal ending, NASA's Fermi Gamma Ray Space Telescope detected a short gamma-ray burst from the same position in the sky. Over the next 11 hours, astronomers coordinated across more than 70 ground-based and space-based observatories and found the optical counterpart, a faint, rapidly reddening transient called AT277D, in the galaxy 4993 in the galaxy NGC 4993, about 130 million light-years away in Hydra. It was the first time gravitational waves and electromagnetic radiation from the same event had ever been detected simultaneously. Spectroscopic analysis by the European Southern Observatory's X-Shooter spectrograph, published in Nature in October 2017, confirmed that the signal matched predictions for a kilonova, a radioactive forge powered by the decay of heavy elements synthesized in the collision through the rapid neutron capture process that fret the astro. The spectra confirmed lanthanides including strontium, gold, and platinum. The event resolved a long-standing debate in nuclear astrophysics. Every heavy element heavier than iron on the periodic table, including every gram of gold and platinum that has ever existed on Earth, was forged in events like GW 17017E0817. 2 neutron stars tearing each other apart at 30% of the speed of light and scattering their cores across interstellar space. Number 1. Galaxy collisions. The antennae galaxies, NGC 4038, and NGC 4038 and NGC 4039 in the constellation Corvus, about 45 million light-years away, are 2 spiral galaxies that began colliding roughly 600 million years ago and are now deep into the process. Observations by Hubble, the Chandra X-ray Observatory, and the Spitzer Space Telescope show what galaxy collisions actually produce. Not primarily destruction, but massive star formation. The collision has compressed giant molecular clouds throughout both galaxies and triggered the formation of over 1,000 young, massive star clusters, some holding millions of stars over timescales of tens of millions of years. Chandra's X-ray data identified hundreds of ultraluminous X-ray binaries, stellar mass black holes consuming companion stars, concentrated in the collision zone. The antennae collision is modest by cosmic standards. The Milky Way and Andromeda, M31, are approaching each other at about 110 kilometers RISSS. In 2012, a team led by Roland Vandermarle at the Space Telescope Science Institute published Hubble-derived proper motion measurements confirming a direct collision in about 4-5 billion years. Simulations run at the Harvard-Smithsonian Center for Astrophysics show the merger will play out over hundreds of millions of years, that individual stellar collisions will be extraordinarily rare despite the sheer number of stars involved. and that the Sun will likely survive but end up in a new orbit in the outskirts of the merged structure. That merged structure already has a name, Nocometa. Subscribe for more, hit the like button, and leave a comment. I read every one.